All right, the previous video talked about how to find pH, pOH, hydrogen, and hydronium concentration in strong acids and bases, and this one's going to talk about weak acids and bases. So essentially we're looking at problems 3 and 4 from this worksheet. So I'm going to rewrite them and then we're going to solve them. All right, we'll start with this hypochlorous acid right here. Since it's not one of our 7 strong acids, it is a weak acid, and thus we need to know what the Ka is. So anytime we're dealing with a weak acid or a weak base, we should talk about how it dissociates in water, because that's what the Ka is telling us. Specifically, that HClO or HOCl plus water is going to, arrow in both directions, is going to break apart into hydronium, because after all, it's an acid, so it's going to donate one of its hydrogens over here to water, and then that's going to leave its conjugate base, OCl minus, left over. So we know initially that we're starting with our 0.00125 molar. We don't worry about water's concentration since it doesn't change, and initially, before it dissociates, we have no concentration of either one of our ions. However, when it does dissociate, we're going to lose some of our original acid, and we're going to gain those ions in solution. That will be our change. So our equilibrium concentration will be 0.125 or 0.00125 molar minus X for the weak acid, and then it will be X for each one of the ions. So since our Ka value is given as 3.5 times 10 to the negative 8, then I'll use that. The reason I'm using the Ka here is because, not just because it's given, but because this is an acid. And as I can see, when it hydrolyzes, it creates the hydronium ion. So it is the Ka value that I am going to be interested in here. So I will go ahead and solve. In particular, I'll set this equal to x squared over 0.00125 minus x. Go ahead and solve. When I used the quadratic formula, I found that x was 6.6 times 10 to the negative 6th. Now, x, remember, is both of these things. It is the hypochlorite ion, but it is also, and most importantly, the hydronium concentration, or in our case, the hydrogen concentration. So we just found the hydrogen or hydronium concentration, from which we should be able to find pH. pH, remember, is the opposite log of the hydronium concentration. So for us, that's going to be the opposite log of 6.6 times 10 to the negative 6. So when I solve, I get a pH of 5.18, which shouldn't be surprising since after all, this is an acid. So to find pOH, remember, we know that pH and the pOH should add up to 14. So pOH is going to be 14 minus the pH of 5.18. So we should end up with 8.86. Once I know the pH and the pOH, I could use either one of those to find out one of the ion concentrations. The only one I don't know is the hydroxide concentration, which can be found from the pOH. In particular, 10 to the negative pOH, in our case negative 8.86, should be equal to our hydroxide concentration, which is, I get 1.38 times 10 to the negative 9. All right, let's see if we can do the same thing for a base. It's really the exact same process. So I am told that I have this concentration of ammonia. I should recognize that ammonia is not one of my strong bases or acids, so it must be weak. In particular, we should recognize it as a weak base. So that means since it's weak, I'm going to have to worry about what it does in water. It's not going to completely dissociate. So I write the reaction of ammonia in water, just like we do with all of our materials. Now, ammonia is most likely going to, as a weak base, it is going to accept a proton, and it's going to make the ammonium ion. And it's going to leave an OH minus in solution. So this is our reaction. So the value I'm interested in is Kb, not because I told you what Kb is, but because I'm clearly making a base here. So when this base goes into water and makes a base, it is the Kb value that I am concerned with. So what we do is we do the same thing we just did. We know our initial concentration is 0.0125 for our ammonia, and none of the ion has been created before dissociation. But as soon as it dissociates, we have a change. We're going to be losing some of our ammonia and gaining our 2 ions from dissociation. So just as we saw, I'm going to have the same setup, my 0.00125 minus X, and then X is going to be my concentration of each one of my ions. But again, since this is a base, I'm worried about the Kb value of 1.8 times 10 to the negative 5. That is going to be equal to X squared, the sum of my 2 products, over my 0.00125 minus X. So I solve. When I do so, I get that X is 1.4 times 10 to the negative 4th. But remember, what is X? Well, X is the ammonium concentration and the hydroxide concentration, but it's the hydroxide concentration that affects pH. So that's what we'll say that we also have. It's the most important part. So now that we know the hydroxide concentration, we can find things like pOH. We can take that opposite log of 1.4 times 10 to the negative 4 and get a pOH value. I get 3.85 for my pOH. So finding pH is easy. It's just 14 minus my pOH of 3.85, so I get up 10.15, which shouldn't be surprising, because after all, it's a base, so my pH should be greater than 7. The only thing I don't know so far is my hydrogen concentration, which, since now that I know pH, I can find by taking 10 to the negative pH, or 10 to the negative 10.15. When I do so, I get that hydrogen concentration, and I get 7.1 times 10 to the negative 11 power. All right. So anytime you have a weak acid or a weak base, you're going to have to make sure that you set up a Rice table. In particular, if you're talking about a weak acid, you're interested in knowing its Ka value. If you're talking about a weak base, you need to know its Kb value, and that's how you'll solve.